Chapter 7, Boiler Water Treatment. Section 7.1, Boiler Water Conditions. After this section, you should be able to describe both feedwater and dissolved solids and describe common conditions caused by poor water quality. Boiler water conditions and water treatment vary depending on the source of water and general operating conditions. Feedwater is water that is treated for use in the boiler. Boiler water is water in the boiler that is used to produce steam. Water, regardless of its source, requires treatment. Rainwater accumulates chemicals, gases, and particles as it falls to the ground. Standing water accumulates solid and gaseous pollutants on its surface. Groundwater contains dissolved solids from the minerals and dissolved gases. Dissolved solids and impurities such as calcium, silica, and iron that have dissolved into solution. Drinking water, also known as potable water, also requires removal of solids and gases before use in the boiler. A boil out is a process of boiling a solution of water and cleaning chemicals in a newly installed or repaired boiler. The cleaning chemicals are replaced with fresh water after the boil out procedure is completed. After initial startup and boil out procedure, a water treatment program to be followed during normal operation is established. Whenever working with boiler cleaning and water treatment chemicals, proper PPE must be worn, including eye and face protection, gloves, and other required protective clothing. Other specific water treatment procedures may be required after certain boiler maintenance. A water treatment program is developed to reduce the possibility of scale, corrosion, caustic embrittlement, priming, carryover, and foaming. Scale is the accumulation of minerals, such as calcium and magnesium, on the water side of boiler heating surfaces. All city water and most other water sources contain scale-forming minerals, such as natural salts and silica. Calcium and magnesium account for the majority of scale formation from hard water. Hard water is water that contains large quantities of dissolved minerals. The hardness of water is measured in parts per million. When boiler water turns to steam, residual minerals are left in the boiler. Scale acts as an insulating material and reduces heat transfer efficiency. Scale also narrows the inside of the tube and restricts the flow of boiler water through it. This further reduces heat transfer. If the boiler water does not remove heat from the heating surface as designed, the heating surface overheats. Scale is prevented by adding chemicals to the feedwater. The chemicals change calcium and magnesium into a non-adhering sludge to prevent scale buildup. Removal of this non-adhering sludge is best accomplished when a boiler is under a light load. Under a light load, the non-adhering sludge is kept suspended in the boiler water and does not settle out on the boiler surfaces. The non-adhering sludge will collect near the bottom of the boiler and can be easily discharged out of the bottom blowdown valve. Corrosion is the rusting or pitting of boiler metal. Corrosion weakens boiler metal by the thinning or removal of the metal, and corrosion causes pitting and channeling of the metal, which results in thinning tubes, piping, and other boiler components. Corrosion is primarily caused by oxygen in the boiler water. Feed water is treated to remove the oxygen by heating and/or chemical treatment. Priming is a condition that occurs when large slugs of water are carried into the steam lines. Carryover is a condition that occurs when small droplets or particles of boiler water are carried into the steam lines. Both of these conditions can be caused by a high water level in the boiler. Priming and carryover can also be caused by high concentration of chemicals. Also impurities in the boiler water that cause a high surface tension, such as oil, or opening the main steam stop valve too quickly. High surface tension is a boiler water condition in which the surface of the water is strengthened by a layer of impurities. High surface tension restricts the release of steam from boiler water and is indicated by a rapid fluctuation of the level in the gauge glass. The gauge glass fills and empties rapidly, indicating bubbles trapped or foaming in the boiler water. Care in opening the steam valves prevents carryover caused by sudden pressure changes. In addition, priming and carryover or a failed steam trap can lead to water hammer. Extreme water hammer can cause steam lines to burst. Foaming is a boiler water condition caused by formation of steam bubbles trapped below a film on the boiler water surface. This is commonly caused by high surface tension from impurities such as leakage of fuel oil in boilers using number 4, 5, or number 6 fuel oil. Fuel oil contaminated boiler water increases surface tension, leading to foaming. Foaming prevents proper heat transfer of heating surfaces, causing dangerous overheating. This can result in blisters and bags forming on the tubes, burning out. Checkpoint. Number 1. What is feed water? Feed water is water that is treated for use inside a boiler. Number 2. What are dissolved solids? Dissolved solids are impurities such as calcium, silica, and iron that have dissolved into a solution. Number 3, what is the difference between scale and corrosion? Scale is the accumulation of minerals such as calcium and magnesium on the water side of the boiler heating surfaces. All city water and most other water sources contain scale-forming minerals, such as natural salts and silica. Corrosion is the rusting or pitting of boiler metal. This is primarily caused by oxygen in the boiler water. Number 4, how are priming, carryover, and foaming different? Priming is a condition that occurs when large slugs of boiler water are carried into the steam lines. Carryover is a condition that occurs when small droplets or particles of boiler water are carried into the steam lines. Both of these conditions can be caused by a high water level. Priming and carryover can also be caused by a high concentration of chemicals. Impurities in the boiler water that cause a high surface tension, such as oil, or opening a main steam stop valve too quickly. Foaming is a boiler water condition caused by the formation of steam bubbles trapped below a film on the boiler water surface. Foaming is commonly caused by high surface tension from impurities such as leakage of fuel oil in boilers using number 4, 5, or number 6 fuel oil. Section 7.2, Boiler Water Analysis. At the end of this section, you should be able to explain the purpose of boiler water analysis and describe the common measurements made when analyzing the boiler water. Boiler water analysis tests the condition of the water and is used to determine the feed water treatment required. Boiler water is analyzed to determine the frequency of blowdown and the amount of chemicals necessary. It is commonly analyzed for proper alkalinity, hardness, and total dissolved solids. Alkalinity is the ability of a compound dissolved in water to neutralize acids and is indicated by its pH level. A solution with a pH greater than 7 is alkaline. Boiler water pH requirements vary, but the pH value of boiler water typically should be maintained between 10 and 11.5 to prevent scale formation. High alkalinity can cause caustic embrittlement. Caustic embrittlement can cause metal to crack along the seams and at the ends of the tubes in a boiler. Alkalinity of boiler water is typically controlled by adding sodium hydroxide, also known as caustic soda, to the boiler water. Hardness is the amount of dissolved calcium and magnesium in water. Water hardness is commonly checked with an electronic hardness tester. A sample is sent through the instrument, where a reagent is automatically added to the sample. The reagent causes the sample to change color. The color change is measured and the hardness is indicated on the instrument panel. A reagent is a chemical used in a water treatment test to indicate the presence of a specific substance. A titration test is a water treatment test using a reagent to determine the concentration of a specific dissolved substance. A sample is collected and poured into a titration casserole, and a reagent is added to the sample. A color change indicates hardness. A quicker but less accurate method of determining water hardness is a soap test. A soap solution is added to a sample. When shaken, the solution of soap and hard water does not produce and keep as many suds as soft water. The soap solution test only approximates water hardness. The TDS present in boiler water can be measured with a conductivity meter. A conductivity meter is an instrument used to determine the TDS, total dissolved solids, present in boiler water. The more dissolved solids in the water, the higher the conductivity. The ASME code publishes guidelines detailing acceptable conductivity limits for specific pressures and temperatures before problems can occur. The boiler water is treated using external and/or internal treatment according to analysis data and standard plant water treatment procedures. Boiler water tests and water treatment activities are recorded in a water treatment log, similar to a boiler room log. Boiler water samples are tested at the plant or sent to a water treatment company for analysis. The most efficient boiler water treatment program is based on accurate daily testing by the boiler operator. Checkpoint. Number 1. What is the purpose of boiler water analysis? The purpose of boiler water analysis is to test the condition of the boiler water and use the results to determine the feed water treatment required. Boiler water is analyzed to determine the frequency of blowdown and the amount of chemicals necessary. Number 2. What is pH? pH is a measure of the acid-alkaline balance of a solution and is indicated on a scale from 0 to 14. Number 3. How is conductivity measured? Conductivity is measured with a conductivity meter. A conductivity meter is an instrument used to determine total dissolved solids, TDS, present in boiler water. And number 4. What is recorded in a treatment log? Boiler water tests and water treatment activities are recorded in a water treatment log, similar to a boiler room log. Section 7.3, Boiler Water Treatment. At the end of this section, you should be able to describe both external and internal boiler water treatment, identify blowdown types and their purposes, and list the goals that a water treatment program is intended to accomplish. External boiler water treatment is treating water, or feed water, before it enters the boiler. Oxygen and non-condensable gases can be removed by heating the feed water. The gases are then vented to the atmosphere. Heating the feed water also reduces thermal shock from water fed to the boiler. Feed water treated before entering a boiler contains all or most of the scale-forming minerals causing water hardness. Pre-treatment equipment is equipment used before boiler water treatment chemicals are added to feed water directed to the boiler. Pretreatment equipment commonly includes filters and water softeners. Filters installed in the makeup water line are available for removing free chlorine, some dissolved organic material, and sediment. They can also remove suspended solids, sand, and iron. Different filters are designed for removing specific material. Inlet and outlet water pressure gauges indicate filter condition and proper function. A water softener is boiler water pretreatment equipment that is used to remove calcium and magnesium to reduce hardness. Many types of water softening systems are available, but the most popular and widely used water softener is a zeolite water softener. A zeolite water softener softens water by replacing calcium and magnesium with sodium. Zeolite is the mineral group that includes silicates of aluminum, sodium, and calcium used to soften water. The zeolite process is performed at ambient temperature in a water softener. The unit is regenerated by passing brine is a salt solution, from the brine tank over the zeolite in the resin bed when the sodium in the softener is depleted. Salt is periodically added to the brine tank to replenish the amount of salt in contact with the water. Boiler feed water usually contains oxygen and carbon dioxide in dissolved gases. Dissolved gases that are not removed before entering the boiler are liberated by heat and can cause severe corrosion in the boiler, steam lines, and condensate lines. This damage can be very costly and lead to dangerous conditions. Dissolved oxygen and carbon dioxide can be removed with chemicals. Depending on the system, it may not be practical to chemically remove the dissolved oxygen and carbon dioxide from the feed water. In these cases, a deaerator should be installed. If plant conditions do not warrant the use of a deaerator, a packaged feedwater system is commonly used. A packaged feedwater system is a tank, pumps, and controls used to heat the feedwater. The feedwater is heated to a maximum of 210 degrees Fahrenheit for reducing the amount of dissolved oxygen and carbon dioxide in the feedwater. The tanks have an epoxy lining or are made of galvanized steel and are vented to the atmosphere. A packaged feedwater system is not as efficient as a deaerator, and more chemicals are required for treatment than with a deaerator. A surge tank is a large condensate receiver that is used to collect condensate before it is directed to the boiler or deaerator. A surge tank is used if there are intermittent peak loads of condensate that can exceed the surge capacity of the deaerator, such as varying pressures or temperatures in condensate, or condensate that does not have sufficient pressure to enter the deaerator on its own. Surge tanks are commonly lined with an epoxy coating to prevent corrosion and are vented to the atmosphere. The temperature of the condensate and makeup water blend depends on the percentage of each. Each manufacturer can combine a deaerator and a surge tank into one package with a common wall between the two. Chemical feeders can be classified as bypass feeders and chemical feed systems. A bypass feeder is a water treatment accessory that introduces water treatment chemicals in a loop. The inlet of the bypass feeder is on the discharge side of the feedwater pump, and the outlet connection is the inlet of the feedwater pump. The pump forces a portion of the feedwater through the bypass feeder, discharging its contents back into the feedwater. Bypass feeders are commonly used on smaller boilers in plants where the load is constant and makeup water demand is low. Water treatment chemicals are added as required by the boiler operator. The inlet to the bypass feeder is installed on the discharge side of the boiler feedwater pump. Valves are opened and closed by the boiler operator to control the amount of chemicals added by the bypass feeder. During normal operation, valve 1, valve 2, and valve 3 are closed. A drain valve is opened slowly to ensure that there is no pressure in the bypass feeder. The drain is then closed. Pressure is present only if valve 1 or valve 3 is leaking. To add chemicals using a bypass feeder, the drain valve and valve 2 are open to drain the tank. The drain valve is closed and water treatment chemicals are poured into the funnel. A lot of times these bypass feeders, what we would call them in the plant, was a pot feeder. And it's just a very crude method of adding water or the chemicals to your boiler. It's just not an efficient way to do that. Feed water chemicals are mixed in the mixing tank. Chemicals are added to the mixing tank as required by the boiler operator. A small pump on the bottom of the mixing tank discharges the chemical mixture through the pipelines to the boiler. Pump output can be adjusted to control the amount of chemicals fed to the boiler. A chemical feed system can be used to feed the boiler continuously, taking as long as 24 hours to empty the tank. In some chemical feed systems, controlled amounts of water treatment chemicals are added directly from drums provided by the water treatment company. A bottom blowdown is most effective when the boiler is under light load and feed water input is also low. The two valves commonly used on a bottom blowdown line are the quick opening valve and the screw opening valve, or also called a slow opening. The valve located closest to the boiler is usually a quick opening valve. This is opened first. The slow opening valve located farthest away from the boiler is opened last. After the bottom blowdown is complete, the valves are closed in the reverse order. The slow opening valve, located farthest away from the boiler, is closed first. The valve located closest to the boiler is closed last. So this is set up and designed the same way in the lab at MATC, where you have your quick opening. That quick opening valve, there's built-in redundancy in these systems where you would open that quick opening valve first, then all of that pressure from the boiler water and the contents is against your slow opening valve. And that's exactly what it does. It's a slower opening valve meant to take the pressure of the boiler and its contents. So if a valve is going to fail, the one that really should be failing first would be your slow opening valve, since that's the one doing all the work, right? So you open that all the way, then you're never going to walk away from this process. Once you start your bottom blowdown, you're going to open your quick opening. Directly after that, you're going to open your slow opening valve all the way open. And then once you go all the way open, you're going to immediately start to close down on that slow opening valve. You're going to close that, and then you are going to close your quick opening valve, and your blowdown procedure would be completed. The water treatment service must be taken into consideration: the system size and design, equipment specified, and the ability of the plant personnel to monitor and maintain the system. The consultant should monitor the in-house water treatment analysis program performed by the plant personnel. Training sessions should be required to familiarize plant personnel with the water treatment system, practices, and procedures. It's very typical in a larger facility where operators on each shift would be performing a water analysis, would be taking a sample of boiler water or condensate or both, and then you would take your water samples and you would conduct your tests accordingly, depending on where you're at and how much money this water company would charge. I'm familiar with the weekly, maybe like a midweek, water tech would come in and do a more extensive testing procedure, and I would make sure that I would talk to the chemical person and see what readings he or she would get and compare them with mine to see if I'm taking the proper readings and doing the proper analysis as I should. So it's just a good practice to get into and keep an open line of communication with that contact that you would have. Okay, checkpoint. Number 1. What types of equipment are used for external boiler water treatment? Types of equipment used for external boiler water treatment include pre-treatment, such as filters and water softeners, deaerators, packaged feed water systems, surge tanks, and chemical feeders. Number 2, what is internal boiler water treatment? That is treating boiler water after it has entered your boiler. For example, in the lab, we are treating that boiler water in the feed water tank. So the feed water storage tank is above our feed water pumps. That's where the chemical is being treated. So we would call that an external boiler water treatment. Number 3, what is the difference between bottom blowdown and surface blowdown? A bottom blowdown is performed regardless of whether or not continuous blowdown is employed. Continuous blowdown is performed for the purpose of removing total dissolved solids, TDS, or other impurities that have concentrated near the surface of the boiler water. Maybe you have a foaming issue. Foaming would be caused by oil getting into your boiler water. And you would want to remove that to give yourself an accurate water level reading. Bottom blowdown is performed to remove the sludge and sediment. And sludge and sediment at low loads would stay in suspension and it would fall near the bottom of the boiler, and you would remove it with a bottom blowdown. That's to control high water. You would use that. Control your chemical concentration in the boiler. There's multiple reasons why you would open the bottom blowdown, but primarily it would be for sediment and sludge, to remove that and control your high water level and your chemical concentrations. Number 4, what is the procedure for opening and closing bottom blowdown valves when performing a bottom blowdown? Well, you would first open the valve. Your quick opening valve would be open first. That's the one closest to the boiler. Then you would open your slow opening valve second. That slow opening valve would be closed first, because remember, that slow opening valve is taking the brunt of the boiler water and the conditions, and that boiler water is beating against that slow opening valve. So you want to always ensure that valve furthest away from your boiler is taking the beating. So that slow opening valve is opened second, right? First you would open your quick opening, second would be your slow opening, then you would close that slow opening, and the last valve that you would shut would be your quick opening closest to the boiler. Another good thing about the redundancy in that system with those two valves is if that slow opening valve starts to leak, well, you can take that out of service without having to drain your boiler and take your boiler out of service. That quick opening valve should be able to hold back all the contents of your boiler, and you would be able to make that repair while your boiler remains in service.